show you what I mean. Okay, we started recording, but like examples of a busy slide, right? This is very busy. A lot going on there. That really should be 2 slides. I enjoy the whale. And a lot of these should be, you know, all busy slide, very busy slides, right? So we talked about, as we cycle through devices, we talked about cyclotrons and the Hall effect, and the things we talked about with these devices were really situations in which you have both an electric field and a magnetic field. Now they both have different sources, but they can be applied to a charged particle, and interesting things can happen. And we discussed that. We sort of went through our devices. The big thing we saw with the Hall effect, right, was that we could predict that the charge carrier was negative. We could see the difference between having a negative and positive charge carrier. We did that twice last week. Once a little, you know, busy with the slides, and then we worked it out with the opposite case to show that we could actually do the experiment. So that was pretty cool, and we proved charge carriers are negative. If you want to see that or go over that, the video should be up and running. And we talked about cyclotrons and talked about mass spectrometers and cyclotrons and synchrotrons as devices that can be used to measure the fundamental properties of the universe or of particle physics. That's really the way of looking at that. But now we want to get a little more streamlined again. So we're still going to be busy, have busy slides with this chapter. But the good news is we are almost done with it. But now we're going to get to a little, you know, we're going to sort of bring things back to Earth. And we talked about a little bit about magnetic fields at the beginning of the chapter. Let me go and we want to go to sharing files. Oh boy. So what I want to point out is that unlike electricity, where we talked about, well, no, I guess we did here. So we talked about the force almost immediately in terms of the magnetic field. And unlike the electric force, right, which we could do entirely, we didn't need a field, right? You'll remember for the electric force, we had, hold on. We had Fe for Coulomb's law equals K Q1 Q2 over R squared. Now you'll notice we did this first, and then we had F is equal to QE, and we were able to derive this electric field from Coulomb's law. Whereas here, we start with the force that depends on the magnetic field first, and now we're going to be able to decompose, our goal will be able to decompose the magnetic field in terms of sort of elementary objects without forces. But, however, that being said, we want to come up with, before we do that, that will be really the goal of the next chapter, but in order to sort of take that step, we want to look at how magnetic forces depend directly on currents. All right? So you might be able to see it right from here, but you might not. So let's go back to where we were, and we'll start with F equals QV cross B, and we will, oh, we're going through the whole thing again. Let's not go through the whole thing again. We want to start here. So you'll notice that you have this new seeming expression for the magnetic force, but we can derive this quite simply from our original force equation. No, that was wrong. Right? So you'll notice here if we have FB equals QV cross B, right? That's going to equal Q dx dt cross B. And we can look at this and say, we can move this around and say that equals dq dt times x. But we don't want to call that x, so we're going to rename this. I'm going to just call it L cross B, and that equals I L cross B. Okay, where the L here is this is a vector, and the B is a vector. Oh dear, now it's gotten it, selected everything. So you can see here, right? I'm going to actually see if I can unselect everything. No, it's all poop. So you can see here that we get the expression FB equals I L vector cross B in a fairly straightforward manner. And what that does is it allows us to look at the force as it directly relates to current instead of charge. And so I'm going to go back and forth so that I can get this highlighted view off. And you'll notice that we can actually look at how magnetic fields respond to wires. All right? So if we have a straight wire, and you'll notice that the magnetic field here is coming out of the page, we can tell which way the wire will deflect by using the right-hand rule, right? So put one of your hands on, so it's L cross B. So you have your L, your length across the wire, the way your current's going. So put your hand flat. So if you're looking at the computer screen, turn your palm so it's facing your head. Put your hand on the picture and the current, and have your fingers point the way the current's going. So if your current is going up, right, now you put your fingers going that way. You curl your hands towards the magnetic fields. This would be towards you. You stick out your thumb, and you'll notice you get what happens in B. That gives you the force, direction of force. All right? Now, you can do the opposite and try to see if you can get the answer for C on your own. Okay? And you just do the same thing. So here the length, because current isn't really a vector, even though it has direction and a magnitude, it doesn't really transform like a vector. So you'll notice we have this L is the vector. So the direction of the current sort of packs it in there, that L, and that's what we consider that. So you usually have to know the length of this wire to figure out the magnetic force. Now, if the wire is not straight, all right, if you don't have a straight wire and it's curved, you will have to take not the whole force, but a differential force, dF dB, all right, and you'll have to add up little segments of dL and then of course, when you integrate it, you'll get the entire force dB. So be careful. We're going to see in this chapter, the next chapter, these equations are going to get a little yucky. I think usually when I get observed teaching this chapter, I often say, because I've been observed twice teaching it, it's sort of like the driest, most math-heavy topic, sort of starting at this part of chapter 28 and into chapter 29. Okay? So let's take a look at how an engine works with torque. What we can do now is we can create a loop of wire in a magnetic field. So it's just sort of extending our previous picture. And when this happens, you'll notice, let's write down the equation again. Oh, I forgot to make that silent. See, I miss calls when it's silent. I don't miss calls when it's not silent. All right. So we can look at force, magnetic force is equal to I L cross B. So let's do a little bit of analysis here. You'll notice when you're on these two sides, right, of the wire, I is parallel, or rather L is parallel to B. If L and B are parallel or anti-parallel, then IL cross B is going to equal 0. So we already know these two sides don't have a force, a magnetic force. So that's pretty cool. It's always fun when something's 0, right? Now on this end, you'll notice that the current travels around the wire in opposite directions when you're just looking at these two wires here. And you'll notice that that creates a force if you use your right-hand rule. And I want you to try practicing. See if you can get the right-hand rule to give you the direction of the force. And that for this wire, it will be going up. And on this wire, it will be going, with the current going this way, it will be going down. All right? Do it for a minute and see if you can make it make sense. You don't have to do it too long, just for a minute. Well, remember, use it on this picture, right? So put your hand, so the first current is going down, right? So try and orient your hand. I wish I could do this so you could see me doing it on the screen, because that's really the only way to, that's the best way to see it. That's what we do in class. But if you get your hand and put it on the wire, right, the one that's on the left, and you put your hands coming out, they should be facing you. Well, you actually have to turn it so that you can curl, because you need to put your hands in orientation that they can close in the direction of the magnetic field, right? And then you'll see if you have that, you'll stick your hand up and you should have that positive Y direction, right? So if it's coming out this way and you're curling it, you should have that positive force up. And if you flip the direction, you'll get that negative force down. So hopefully you've gotten it to work. If not, all I can tell you is thumb is the direction of the force. Good, yeah. But what I want you to see is, so keep working on it if you haven't. That's okay if you're struggling. Keep working at it. You can see here that with one force going this way and the other one going the other way, are these two forces going to cancel out and lead to no motion? Oh, be very careful. They're not applied at the center of motion, Mustafa. The center, if they were applied at one point, you would be correct. But one's applied at one point and the other's applied at the other. So it will twist. It will rotate. All right? And this is basically a simple magnetic engine. All right? You can just get a current running around, and then that will, in a magnetic field, it'll start rotating. Now, the torque is defined as R cross F, right? Okay, well, take a look at my pen here, right? Well, let me move back. Can you? Or you know what? Let me, here, I'll use a DVD cover. Can you all see the DVD cover? It's season 8 of Scrubs. Here, I'll put it here so you don't have to see maybe my poor choices. Now, if you have one force pulling up on one side of the DVD and then another one pulling down, it's going to facilitate rotation. All right? Do you see that? Does that make sense? Good. All right, that's what we're looking at. Put my DVDs back. I have a project, digitizing my library. So, when we look at our original thing for expression for torque, we can rewrite this as R cross IL cross B, right? And we know that we're going to have a perpendicular, that for this cross product here, we're going to have something that looks like ILB sine 90. That's going to be 1 because they have to be perpendicular for this to work, right? We're only looking at the perpendicular component. And then we can look at the whole thing and see that the magnitude of the torque, at least, will be equal to R times L, IB, and then whatever the angle is between R and, I'll use theta since they use theta. Okay, now you'll notice the only thing they did here is they added two terms. One is they combined the R times L to get this A term, this area term. That's where that comes from. And then N, usually this is a nice picture, but usually when you're doing something like this, you have a number of windings. So you go around many, many times. And there you would multiply the number of windings, which is N, or turns in the coil, times the current, times the area, times B, times the theta angle between R and F. Okay? And that's you know, we're going to see more applications that look like this, and this is basically how, you know, the start of our understanding of electric or magnetic motors. So that's good. The magnetic dipole moment has a lot of stuff going on in it, but it is we're going to see that it's a little, it's a little bit like the electric dipole. So a magnetic dipole, all magnets sort of come in dipoles in these dipole flavors. And we can look at the torque as mu cross B, where mu is this magnetic dipole moment, and mu will be that first part of that triple cross product, right? Remember, we had R cross IL cross B. This is torque, so we can infer here that mu, and you'll notice that it's a vector here, right? It's going to be equal to R. No, this should be equal sign. I don't want to confuse everybody. Should be equal to R cross IL. Okay, and much like we saw with the electric dipole, we can store energy in the magnetic, or sort of in the magnetic field, or in these dipoles, by looking at the dot product of the magnetic dipole moment and the magnetic field. Now, where this becomes important is when you look at how something is orientated, right? If we go back to the last slide, you can see that you can, there's a lot of stuff there. You can see that you can orientate this, and you can sort of store energy in these currents. You can orientate it so that there is an orientation where it won't move, and then an orientation where it'll keep spinning. Okay? And that I would implore you to look at yourself. And that will do it for chapter 28. So we want to move on to chapter 29. So it's a good time to sort of pause and see if, excuse me, if we have any questions. So induction will be its own thing. So it's sort of the beginning of understanding induction, but induction is, we're beginning that process. So this is the foundation of it, but it is not induction itself. Induction requires two systems interacting together, whereas this is just a magnetic field applied to a current loop, and it's causing it to spin directly. In induction, changing magnetic fields will cause things to change. Here, the magnetic field could be constant, and the inertia will keep the motor spinning. We will talk about induction motors as we go forward. Okay, so they will be a good time. That was a lot of coughing. All right. So let's go on to chapter 29. So as you can see, we ended the last chapter talking about magnetic fields due to currents, and now we're really going to explore it. But we looked at long straight wires before, but you'll notice that we're going to focus on the fields, not so much the forces. All right? We'll have some stuff there, but now we're going to finally sort of see like the nuts and bolts of the magnetic field. All right? So when we look at it here, as always, we want to look at the basic systems. We want to look at some arbitrary wire, I just noticed my pointer was non-working, right? The current can just twist and go along this wire and be stuck in that wire. That's fine. No real issue there. But you'll notice that when things are complicated, we do what we always do, which is take a short, tiny little bit of it that looks straight, and we'll call that DS. All right? And so now we want to get an idea of what the problem is that we're going to set up. So the problem we want to look at, what's generally being looked for, is that we know that this current, there will be some magnetic field due to this current at some point. All right, so looking here, we're saying that the magnetic field in this particular case will be into the page, but we're at some distance away from the wire. We want to look at the current that's causing this magnetic field. So you'll notice that there's a distance r in this r hat direction. Now, if you took me for physics 1, I'm hoping your physics teacher, even if you didn't take me for physics 1, told you that r hat is dangerous territory. All right? Because you usually have to start looking at r hats, then theta hats, and phi hats. This is hard. Basically, the expressions get really ugly really fast when you try and it's like vector trig stuff. It's more like vector calculus. If you try to find generalized expressions for things like acceleration and velocity is not so bad, acceleration's bad. When I was there's this quantity called the jerk, which is the acceleration, the derivative of acceleration, and I was asked to do that in an intermediate class in spherical coordinates with r hats, theta hats, and phi hats. I gave up after 12 pages, and my friend Ethan did the full 20-page expression, and he wrote very small. And the professor was like, oh, well, this thing here, you can reduce it. This thing on page 12 cancels with this thing on page 2. And this thing on page 11 cancels with this thing on your last page. And we were like, it's just like, no, this is not worth it. So the danger comes from things erupting very quickly and not being consistent. You want to be sure you can maintain consistency when you're using it and why you're using it. So we're going to use it in a way in which it makes our lives easier, because we're going to find that our magnetic field will have a cross product of this r hat. But the beauty of a cross product, right, is when you take the magnitude of r hat, as complicated as it may be, it's still a unit vector, so its magnitude is still equal to 1. Okay? So we want to look at our points. We have our I.ds, right? Our IDL, because remember we looked in the last chapter, we had FB equals IL cross B, but we really want to get this B part without relegating ourselves to the force. So we're setting ourselves, so when we look at our setup here, you'll notice we have an R hat, an IDS, and we have that our DS gives us an IDS, a theta, and an R to R hat, this distance to the point we're interested in, okay? And so you might suspect that we are going to use a cross product, and we are. But don't freak out, because when we look at the Biot-Savart law, it's a little harder than your other equations, right, for like electric fields and gravity fields. This is the inverse square law for magnetic fields. It's a little bit of a bear. And this is the generalized version. So not only is it a differential, but it's a vector cross product differential with this. It's a cross product differential where the differential is one of the vectors, where you can see right here. And you have this R hat here. But again, this is where this stuff comes in. The R hat, this is nice because when you just write the magnitude of the differential magnetic field, the magnitude of that R hat vector is going to be 1, so you have IDS sine theta. All right? Now, sometimes this can make things easy, sometimes it makes it really hard. And we're going to see 2 examples of this, okay? So Let me minimize that. There's too many windows everywhere. So, all right. Now, there's a, what is the unit? Oh, we're getting there. So, the unit for the magnetic field is the Tesla, all right? Just like the car and the inventor. So when we're solving for V, so when you're solving for B, that's you'll either see it, you'll usually see it in Teslas, the scientific, the SI unit for magnetic field. Sometimes you'll see a Weber, but you know that's okay. We have a new symbol we've introduced, mu naught. This is the permeability of free space, and it's equal to 4 pi times 10 to the minus 7th Teslas times meters over, is that amps? Yeah, that's amps over amperes. And one of the interesting things we can see here is that, well, we want to relate this permeability back to our permittivity of free space. So recall that we had K for electric fields, right, or for electric forces is equal to 1 over 4 pi epsilon naught. All right, and this epsilon naught was the permittivity of free space. Yeah, Tesla meters per ampere. Yeah. Now, mu naught and epsilon naught are going to be very important, and they're going to fundamentally help us find the speed of electromagnetic waves and have us be able to calculate that as identically, or determine what the speed of light is and figure out what c is identically. And in fact, we can measure c. We can measure these constants independently and theoretically, and use these experiments to relate to light experiments, and that gives a real nice structure for measuring electric, magnetic, and the speed of light, or quantities with the speed of light. So the law we're looking at in particular here for magnetism or magnetic fields is known as the Biot-Savart law. I don't speak French very well, so if you speak better, that's not great. Sorry, email keeps popping up. We just got some bad news. I don't speak French, and this is usually a student does. I'm sure I'm saying it wrong, and I'm okay with that. But this is how we construct this expression for this differential magnetic field, and this is the basic problem we're looking at. Okay? So, questions, thoughts, anger? All right. Lots of anger. Well, if you want to express it, now's a good time. How can I alleviate your anger? Or is it not about magnetism in particular, just about other things? If it's about other things, I'm probably not the best person to help. Yeah, Tesla times meters over amps. Oh, well, with this one takes some time to click. So I want to go over it just again to summarize. So let's first look at the problem. The problem is I have this arbitrary wire and I have a current flowing through the wire. What magnetic field at some distance away will be due to a small part of this wire? So because I'm looking at a differential part of the wire, I'm not looking at the magnetic field due to the whole current, but due to a small portion of the wire. Okay? So what I can look at is the I.ds. I can get the little part of the current. That's how we get that little part there. And then we have the distance, r, that will call to the r hat direction. Yes, it's from a small section of wire. So I'm hoping that this is the problem that is being described by this Biot-Savart law. Hopefully that helps with the anger a little. But I still want to finish what I was going through. So basically, this is the geometry of what we're looking at, and we can formulate and relate that magnetic field to that differential magnetic field to that small current and the distance we are away from it. And you'll notice that, like Coulomb's law and the law of universal gravitation, with magnetism, it's also an inverse square law. But we have these other constants of magnetism. So this is what it would look like. Now, this is the specific case here. And after introducing the permeability of free space constant, we can get a more generalized equation. So basically, for any arbitrary small amount of wire, if you want to figure out that of length ds with the current running through it, you can figure out the magnetic field of it by applying the Biot-Savart law. And we're going to apply it to some simple situations right now. So that's the next thing we're going to do. We're going to see some examples. No, think about it in a computer. Like, imagine you're wiring something, and this is where we're really missing out by not doing this in the lab. Think about whether you could change an electrical system by just changing how the wire is orientated, right? Think about your electrical output. Or think about an object you have plugged in, right? That's the simplest way. If you have a peripheral to your computer, if you change the orientation of the mouse, it doesn't change the electric load coming to the device or anything about it. So the shape of the wire will affect the magnetic field, but the current itself won't be affected by the shape of the wire. Okay? Good. All right. Moving on. So we're going to look at some results here, and we're going to we're going to prove them both. But right now we're going to state them. We're going to state both of them. So you'll notice that for a long straight wire carrying a current, the Biot-Savart law gives for the magnitude of a magnetic field at a perpendicular distance r from the wire this expression. We're going to prove this. Not quite yet. But what we want to do is see what that magnetic field looks like. So you'll notice this is a long straight wire that's going into the board, right? So the magnetic field is, or actually, no, wait a minute. That's the current is going into the board. Now I'm getting confused. So you'll notice that with the magnetic field going in, you stick your thumb, put your thumb pointing there, and your hands curling will give you the direction of the magnetic field. So here, where before your thumb was the force, now your thumb is the current. Your current is sticking in there, and you have that magnetic field. Now, you can also do this the other way. If you have a circular wire, if you look down at B, right, and you have, you want to look at which way the current's going, and then you stick your thumb out. You'll notice here it's going counterclockwise. That will mean the magnetic field is sticking out of the page. As you stick your thumb out, you'll be able to see that. Man, the right-hand rule is not easy to teach in distance learning. I am not looking forward to Physics 1 getting to torque. So this is the curl straight right-hand rule. So let's read it. Hopefully that'll help someone. Grasp the element in your right hand with your extended thumb pointing in the direction of the current, just as I said. Your fingers will then naturally curl around the direction of the magnetic field due to that element. All right, but you'll notice that it can get a little crazy. So try that in these situations, but right now we want to prove these results using the Biot-Savart law. So the first thing we want to do is we'll write it up here at the top of the page, and we're going to do this in opposite order. We're actually going to prove that the magnetic field at the center of a circular arc of some radius r and angle phi in radians is carrying some current is equal to mu naught I phi times 4 pi r. Okay, so this one is pretty straightforward to do. So let's look at, first we always want to write down the law we're working with, right? So we have dB equals mu naught over 4 pi times I dl cross r hat over r squared. Okay, and to make our lives easier, we want to say this as I'm just going to make a dummy substitution from L to S because I like it a little better, and I'm regretting my decision, my choice there. But I can write this as I. I'll keep it DL. Who cares? DL, and then remember the magnitude of R hat is 1. So here we just have sine theta over R squared. Now here, I've just called their ds dl, but that's fine. But I want you to notice, look where my pointer is. I want you to notice, does this, the angle between R hat and ds, does that change as we traverse the curved segment here, as the current traverses the curved segment? Does that change at all? Or will it always be 90? Always 90. Good. So we can write this down here. I want to write here that dB is going to equal mu naught over 4 pi times dl sine 90 over r squared. Now the r squared, this r we can turn into a constant, right? Because we're moving in a curved arc with a constant radius. So r doesn't change, so we can call that big R squared. And now we just have to integrate around the path. So what we can do here is we can integrate on both sides. And we have here then that the integral of dB is b. And that's going to equal mu naught. Sine 90 is 1, thankfully, right? So we don't have to write that again. Mu naught times 4 pi. And then we'll have 1 over r squared, because that's also a constant, times the integral 0 to phi of dl, right? Because that's the length of that arc. Basically, you just, that's a trivial integral, right? And you get mu naught, oh, I forgot the, always forgetting something, I over r squared. Hold on. I missed the Jacobian here. The dl is going to be equal to, I knew something wasn't feeling right. Mainly I knew that because we have an r squared here and an r here. I was like, where did that go? And we missed a Jacobian determinant. That's okay. We didn't miss it, I missed it. So we can write, well, that wasn't all wrong. I shouldn't have erased all of it, but let me see here. Over L dl. Now, that's going to equal to, if we look at this integral, let's take a look at this integral and transform it. So if we're looking up here, the integral of dl, right, is going to be equal to, we want to change this sort of rectangular arbitrary thing into polar coordinates. So the length of that arc will be equal to the integral of r d theta, or d phi. As you can see, phi's and thetas going to get mixed up. Oh, no. This is just a transformation to polar coordinates from calculus. It shouldn't be too weird. But what's going to happen is this will be a fixed r, right? And then we'll have mu naught over 4 pi times I r over r squared, right? Those will cancel. And we have our integral from, we have our integral of d phi. which we can integrate to phi. So when this integrates to phi, you'll have your mu naught over 4 pi. You have your r. We see where that comes from. And we have I, the current, times phi. All right, and that phi comes from integrating around that angle. Okay, so we know for a curved segment where this comes from using the Biot-Savart law. Now, sadly, that is the very simple one. We want to now develop this equation for a long straight line, and I bet you're thinking, how hard can it be? A bit harder. So let's go and look at the derivation, and we'll follow it step by step, and afterwards we'll look at it. We'll justify each step. Okay. So here you'll notice we set up the problem, right, where we have a current. You'll notice this is a infinite wire. A long straight wire means basically infinite. Okay. And you'll notice that we have this ds segment going along the wire, and we have our r hat direction going towards the point we're measuring at. But things change here, right? We know we have this distance, we're picking this point, but our r value will change along the wire. This can be frustrating. And we'll also have this angle will change. A lot of things will change. So much like we did with the electric field, we have to set up everything correctly. So let's see and look at what we're doing here. We're looking at a small dB, right? So we're just looking at this one point, this small length of wire, and we have our Biot-Savart law written in general, right? You'll remember that we could look at the vector equation, but I want to remind you that the integral, or the magnitude of r hat, is 1. So that is the worst one I've ever drawn in my life. It's not every day you get to do the worst at something. There we go. It's 1. So we can start off. So I just want to get sure we're on this page. This is sort of this magnitude of the differential magnetic field once we evaluate that cross product of the Biot-Savart law. All right. But I want you to notice it's very general here. Okay. Now, unlike before where we had sort of this nice finite curved wire, the step that they're not leaving here is that b equals the integral from negative infinity to infinity of dB. But this is a nightmare, right? So what we do is we pick a spot, right? We'll just pick some spot. Let's call it, we'll pick this symmetric spot, and we'll call that 0, that we're symmetric around, and then we'll say that this equals 2 times the integral from 0 to infinity. This is far more manageable than a negative infinity to infinity integral, right? So that's where this transformation comes from. That's where this expression comes from here. All right? So are we all good here? Just this step. Does that make sense? Okay. So when we're doing this, what we integrate on one side, we must integrate on the other side. So you'll notice now here that we have, mu naught times I over 2 pi comes out very nicely, and we're integrating sine theta over r squared. Now, these are a little frustrating because we have these things are sort of always going to change, right? So we have, we want to integrate with respect to s, so things we want, right? Things we now, when we look at this, this value of s changes, but that's not a big deal. That's our x, that's our differential value. So we have one value that can change, but we want s to be the only thing that changes, right? Right now we have a theta that we can see will change as we have different points here. We have an r that's going to change. So things that won't change. So we want to get these two things that do change in terms of just one variable, and our one variable here is s. Okay, so because, and we already know, we can look at our Biot-Savart law and know that that's our dynamic variable because it has a ds right there. That's the one that can change, right? So now if we look at our triangle, no matter where we are on this wire, this distance, perpendicular distance to the wire, r, that will be true for all points. And so what we can look at for any triangle, for any point we have here, we can see that r, or r squared, is equal to s squared plus r squared. Now this is great, right? Because we now have r, this random r, in terms of the thing we want to be dynamic, our s variable, and our constant. All right, so this r doesn't change. So this is good. All right, now you'll notice they solve for r directly and they get the square root of s squared plus r squared. That's not a big deal, but we should be able to get this step. Now you'll notice your angle here is phi, but you'll notice that the sine of this angle should be equal, because they're the same angle, the sine of this angle. And when I mean this angle, we can write this one as pi minus theta. All right, so you'll notice it says here that sine theta is equal to sine pi minus theta. If you don't believe me, play it around with it in your calculator until you're convinced. But because of, we can look at this and say that this is the same sine theta of this angle, which we're interested in, will also be equal to sine of pi minus theta. Well, we can use our triangle again, and we can see that the sine of this angle will be equal to the opposite, right, over the hypotenuse. So when we look at that, we can see that for that angle, the opposite, sine theta, is going to be equal to the opposite, which is r, over the hypotenuse, which is r. This will also be equal to r over r squared plus, or s squared, sorry. Now, as to the 1/2 power. Now, as bad as this looks, right, and this is where this comes from, as bad as these two things look, when we plug them into our equation for b, that integral is pretty difficult. But it makes everything in terms of a constant that's not changing and the one dynamic integration variable we have. All right? So now we can be assured that what we have will go correctly. Now, as far as actually integrating this goes, I'd look it up in a table. That's what I do personally. Use a computer, use Mathematica. If you want to do it by hand, I will stand up and applaud you and throw roses at you, and you can be awesome. But this is the kind of thing where I tell students, if we had an in-class exam, right? If you asked me in an exam to do this integral for you, I'd do it on Mathematica or Wolfram Alpha in a very general way, and I'd just write down the answer for you, which they do here, right? So we just get our integral, or we calc to it, and what we can see here is that if we indeed plug in our two limits, right? So when we look at the value of this at infinity or 0, so at 0 it will go to at 0 we'll have a 0 value. So, and when you go to infinity, you know, you'll basically, as this gets bigger, if you take the limit of it as it approaches infinity, that you should be able to see kind of clearly goes to 1, right? So for large values of s, right, s over, this becomes s squared plus r squared to the 1/2. For large values of s, this goes to 0, and you have s over s equals 1. So for larger and larger values of s, as you get to infinity, the limit of this as it goes to infinity is 1. and therefore you have just the u naught I over 2 pi r part. Okay, and that's where we get you'll notice if you look at this, that is where we get our long straight wire. Now I'll have you know, for a semi-infinite wire, right, you just have the result. So if you only look from, if you're truly only looking from 0 to infinity, you would actually take out that 2, and you just have mu naught I over 4 pi r. Okay? For semi-infinite. Actually, I'm going to use the text function here. For semi-infinite wire. That's better. And we need to make this, nope, that's bad. We can't make that an equality because they're not equal, but we can say implies this for semi-infinite wire. Okay? All right, so I think that brings us to break. Yay! I'm gonna turn off the video for break. Oh yeah, Mustafa, before we go on break, what's up? A semi-infinite wire is, so the last question we looked at, this wire goes to infinity in both directions. All right, so a semi-infinite wire would actually start here. I'm going to make the shape. So it would start at that point and then, you know, go on to infinity. But there would be no wire below. So this wire goes up to positive infinity and down to negative infinity. This wire starts at 0, there's no wire below, and goes up to infinity. Okay? Yeah, right. Well, this is kind of good enough because the idea is if you, it's a good approximation if you look for magnetic fields and your distance here is smaller, much smaller than where you are from the wire, right? So in that sense, it makes sense. In the real world, we'll use Ampere's law to find the magnetic field for it's the remember how we had Gauss's law was sort of a nicer way to solve for these magnetic fields. Well, we're going to see that there's a nicer way to do that in this chapter too. But basically, you can, you know, if you have a, you know, for looking at a very long wire, this helps if your magnetic field is, its distance from the wire is small compared to the length of the wire. How did you go from to RDS in the integral? So from up here, you get this from plugging in. You have these values of sine theta. You plug that right in here. So that's where your r in the numerator comes from. And you get square root of r, a 1/2. And then with r squared, you get r squared plus r to the 1. So that's where this 3/2 comes from. All right, so you just plug r in here, and you plug sine theta in here, and this is what you just naturally get. Okay? All right, good. All right, I'm going to turn off my camera for a little bit, and we'll come back at, oh, I don't know, I guess probably close to 5 after, somewhere between 5 after and 10 after 7. So be available then, and we'll just kind of get going. and then we'll make progress in this chapter. But I'd like us to finish the chapter this week, but that's definitely not today, right? So we'll just sort of keep going until we get there. I think we've made pretty good progress so far, and we have some examples to go through next, I believe. So we'll do that, and I'm gonna plan my dinner. So yeah, I'll see you all in a couple minutes, but I'll keep recording in case something comes up. All right. Okie dokie. Oh, let me turn on my light. That way I can be seen. All right. Okay. Everyone ready to get going again? So the first thing we will do is, now that we've done this, is we will work on a short example. So let's look at this wire in the figure. You'll find in your book that that is indeed figure 29.8. Carries a current I and consists of a circular arc of radius r and a central angle of pi over 2, right? It's the angle there, and two straight sections whose extensions, you notice these are extensions, intersect at this point C. So we want to write the magnetic field magnitude and direction does the current produce. And you'll notice we want to do this in terms of our current I, which could be given, and our radius r. Okay. So the first thing to do in solving this problem is to realize that there are 1, 2, 3 regions. All right, and they're labeled not as I circled them, but 1, 2, and then 3 is the curved region. So let's look at and see where that makes sense. So the first thing we want to do is we want to write down our Biot-Savart law. U naught over 4 pi times over r squared, right? So now keep in mind, we're just evaluating the cross product of I ds cross r hat as the magnitude of I ds times the magnitude of r hat times the sine of the angle between them, and this is 1 because it's a unit vector, right? That is the advantage of using it as r hat. So when we look at this here, we'll you know, what I want to sort of give you the hint of is look at your I, your ds here, and your ds vector, or the angle between your ds vector and your r hat vector. All right. So take a look at that and see if you can figure out, do this example by inspection. All right. So you'll notice that r hat, let's just make that clear. If you take a small section here, your r hat vectors will point towards here. Your r hat vector along here they'll always point to this point C. I'm not drawing them very well, but I hope you get the idea. I want to delete that. All right, the r hat vectors are always going to point to this point C. Okay, and once you know that, hopefully this should be fairly trivial. All right, so I'm going to give you a minute or two, see what you come up with. This is almost like a checkpoint. But again, it's one of those, if you want to chime in, feel free, but don't feel like you have to. I just want you to work on it, and then in about a minute, or at about 7:14, I'll start working on it, and then the idea is for you to think about where you got lost, and if that springs any questions, to ask them then. Okay? So I may as well stick correct. Okay, so again, the trick to this is looking at these r hat vectors. So you'll notice that if we look at section 1 and 2, the IDS vector is always in the direction of the current, right? So you're going to notice that in this direction, it's parallel with r hat. So in section 1, the r hat vector is parallel with the ds vector. All right, this implies that phi equals 0, which implies sine phi equals 0, or sine theta, theta phi, it doesn't really matter. And this eventually implies that B1 is equal to 0. Now, if we look at region 2, R hat is anti-parallel to ds. This implies phi equals 180 degrees. And that implies that sine of phi equals 0. All right, and if you look here, right, you have your current going this way and dr going the other way, right? Or your r hat vector. Okay, and then again, this implies that B2 is equal to 0. So just looking at 1 and 2, right? 1 and 2. Is everyone with me so far? Any questions on that? Nope, it makes sense? Good. All right. So, good. So the vector ds always points along with the current, right? So remember when we look up here, it's I ds. This is a magnitude. So I is always in the direction of ds. So if I is pointing this way, ds in 1 has to point the same way. And you'll notice I is pointing this way now in 2, so ds has to point the same way. Okay? Does that make sense, Anthony? Okay, good. Now, we're not done yet. We've only looked at 1 and 2, but we have that B1 and B2 equal 0. We always like when things equal 0. And this now leaves us with 3. So in 3, you'll notice, right, that ds goes around in the circle in the curve, right? So if we pick any point, it's tangent to the curve, and we're always pointing towards the center. So we're going to have a 90-degree angle. Notice that, I'll go back to theta. Theta is always 90. 90 degrees. So that implies that sine theta is always 1 in 3. And we can then use our arc, right? B will be equal to mu naught I phi over 4 pi r, right? We can look that up from before. And now we just plug in, we were given this phi before, so that equals mu naught I times pi over 8 pi, because phi is equals pi over 2. So because we have that phi, I actually am going to take the effort to change all my angles here. I really was hoping I could be lazy, but laziness comes with a price. Theta. All right. And over r, and the pi's cancel. And we get is equal to mu naught I over 8r. Now, B total is going to equal B1 plus B2 plus B3. I do this because it won't always be this easy, right? Yes, in this case, B1 and B2 will be equal to 0, but it won't always be so easy. Right. Yeah, always start with the if you start with IDS cross R, yeah, well, even if there is a significant angle, and you're just to get the nice thing about this expression is it's always going to pretty much reduce to IDS sine theta, even if the angle is appreciable, because the r hat, the magnitude of this r hat is always going to be 1. This was, even though it looks ugly here, this is the formal version, and if you had a 3-dimensional field, that might get, that might get a little tricky, because you'd have to do several terms, right? And you'd have to keep all the orders correct. But just looking at this and looking at the 1-dimensional version, or along the r hat with just this r hat here, or s hat, being transformed so that it's perpendicular, or that it's just some angle, absolute angle difference between that and r hat. That will usually nicely reduce here. And then when you do that, you just use the fact that the magnitude of that unit vector is 1. And then usually the hard part will be making sine theta and r squared make sense. But yeah. But always start with there. Always start here so that you're just starting in the right place, and you're consistent. Because again, the worst thing you can do is try and start with a simplification and then have it not apply and then get lost. But going back to our last step here, it won't always be this simple, but in this case, it is 0 plus 0 plus mu naught I over 8r. And then so the total magnetic field at point C is mu naught I over 8r. Now, the next thing we have to do is we have to find the direction, right? It definitely asks for the direction. So now we have to use our right hand rule. So we use our right hand, and I can't put my fingers along the direction of the current with my thumb facing towards me. So I'm going to turn my hand around and go that way and stick my thumb out. And with the current spinning what appears to be clockwise, the magnetic field will go into the board. So the 8 comes from algebra, right? So I plugged in pi over 2 for phi, so that gave us a pi on top and a 2 times 4 on the bottom, and 2 times 4 is 8. All right. So if you look here, phi, if you plug in pi over 2, that 2 comes down here and multiplies to 8. All right? So we have this, and we have into the board, or into the screen. Oh, all right. Okay, so take another look at it. Yeah, so you have to use the right hand rule. So I want to align my hands with my right hand with the current, all right? And when I stick my thumb out, you'll notice when I can curl my hand in that clockwise direction, my thumb, if I stick it out, will be pointing into the screen, okay? So sort of like if you can, this isn't gonna help either. There's no way to really visually do it in a good way because it's mirrored with the camera. So it's all gonna be bad. But again, so the Biot-Savart Jesus gives you only the magnitude. All right, you have to apply the right hand rule to get the direction. And so you get your hand. If you just put your hand up to the screen naturally, you'll notice that, well, my fingers aren't going the way the current's going. So you want to make sure your fingers, right, these guys, are curving, can make a circle that goes in the same way as the current. And then you stick your thumb out, that tells you the direction of the field. All right? And so we can see here that because we're moving in a counterclockwise, or no, I'm sorry, a clockwise direction, that our thumb will stick out into the screen. And that's how we get our direction. Okay? Good. All right. The hand, so that's the right hand rule, right? If you want to go back and look that up in the book, you use the right hand rule. The hand curling is the current. The current's moving in a clockwise direction. You stick your thumb out, it should go into the board, right? If you want to draw it on a piece of paper, hold on, this might actually be helpful. Let me get a piece of paper. Give me 1 second. Okay. Let's see. So you go, I don't know now. Oh, come on. That's right. Can you see the circle? Probably barely. I don't have dry erase markers here. I don't have good options. So if you look, my hand, I put my hand going around the current like this. And this should be moving. It might be mirrored, but the whole point is I get my hand to curl with the current, right? You see how my hand's doing that? That's my right hand. So now I close my hand around the way it's curling, and I stick my thumb out. You see how my thumb goes into the paper? That's how we apply the right hand rule. Okay, does that make a little more sense? Oh, there's so many right-hand rules. So many right-hand rules. I'm going to tell you, you'll have to look at them. There's 2 ways to do it, right? It depends whether you have a magnetic field, so you can use the same one whether you're given the magnetic field and you're looking for the current, or the current looking for the magnetic field, right? Because one will be a circle and the other one will be perpendicular to that circle. So as long as you have that rule, you can use them interchangeably between current and magnetic field. It just depends which one you have. All right. So basically, we're going to see that there's probably a grand total of 3 or 4 right-hand rules. You have to know the context, and you have to sort of keep on it, as it were, with the right-hand rules. Okay, that's garbage. All right, I'll throw that out later. I think that's the best I can do. Yeah, you got to use the one that's helpful. They don't all work in the same way. You have to know your context. All right. I'm going to move on from this example now, because we have a little bit more to go. So I would say watch again and send me questions, or we can talk about it a little bit after class too if you want. All right. So now we sort of have this interlude where we can look at the force between two parallel wires. So if you look here, you have two currents moving in these parallel wires, IA and IB. All right. Now you'll notice that things get a little interesting here. The magnetic field, it's hard to picture, but oh God, I really wish I was in class for this. If you look at the pen, all right, imagine this pen is a wire. So if a wire is going, if a current is going down the wire, right, then that will create a circular magnetic field. Okay, so I want to redraw what we're looking at here and have it make sense. So if you look at IA, we're going to make two drawings. So instead of looking at these wires at this angle, we're going to look at them dead on. And you're going to notice we have two currents, right? This is IA, and this is IB. I'm going to change to purple. Now, because these are into the board, they're going to both have magnetic fields, and they're both going to be moving counterclockwise. So let's look at this here. So we'll have a magnetic field from this one that's in a circle, and we'll have a magnetic field from this one that's in a circle. And both these will point that way. Now, this is where things get interesting. Okay? We can look at a similar, I'm going to redraw the picture, but I'm just going to do it slightly differently. We're going to focus here on wire B. Okay? So when we're looking here, and we look at the wire IB, and we want to look at a certain length here, we're going to notice that this is wire B, right? And when we look at the force of a wire, FB on A, or FB, the magnetic field, or the magnetic force is equal to I, right? So that would be I going through B times L times B of the applied field. So let's see what that means. So usually we'd look at, this would be IB. This is the one we're looking at. Now, remember, the magnetic field changes with distance, all right? We won't be able to do the full circles here, but eventually we'll have a circle that hits right here. And so this will be the B field, whose source is the wire A, this one that says current A, that top wire. And so that will be the source of BA, all right? And then we can use our machinery, our Biot-Savart machinery, to find this B and then plug it in here. And that's where you get this equation for the force between two lines, or between two charges. This is really hard to see, and we're sort of getting to the part of the semester that, man, I'm doing the best I can, but I would be much happier in class with you talking about this particular topic. This is tough to see just the way I wrote it, but I think that should be okay. So marinate with that a little bit while I talk about the properties of this, and let me reset my microphone. I was probably screaming, and most of you are, my volume was probably very high. So when we do this, we want to notice a few features, all right? One, that parallel wires carrying currents in the same direction will attract each other. So unlike charges in which opposites attract, right? If the currents are the same, we get that the forces, the wires, will bow towards each other, as you can see here. And if you do the opposite analysis on A, you'll get that they'll come towards each other. Parallel wires carrying currents in opposite directions actually repel each other, okay? And the magnitude of the force on a length L of either wire can be just determined by what we did before. We looked at the physical situation where we have a current, right? So we can look at the magnetic force from the magnetic field on B from A, right? So B of A comes from this wire, and we can look at the magnetic force between the field of A and the current running through B. And that's what we get here. Okay? So one application of this is a high-powered railgun, which we can see here. Now in this case, you have the a conducting fuse that can become a conducting gas and a projectile, and you have a current going up and then down. So in this case, they'll want to repel and push it. They'll want to well, actually, they don't contribute here. Here you have the current going this way to sort of close the loop, and that creates the force pushing the slug up the railgun. All right. So you have this vaporization, and then you have the they'd be going opposite ways. They would repel and push, and that would give that force up. So the general procedure for finding the force on a current carrying wire is the following. All right, to find the force on a current carrying wire due to a second current carrying wire, first, find the field due to the second wire at the site of the first wire. That was that part where we talked about. So when we talked about this, let's review that again because we want to see it. So when looking at the two wires going into the board, we have our wire here we're looking at. One we are looking at. All right, so that's the site of the first wire. Now let's change colors. The magnetic field will emanate from here, and again, as we make these circles bigger, we will eventually come across one. Again, it goes off of the screen. And comes through the wire. That is the field due to the second wire. I'm trying to underline things, not cross them out. All right, but I'm color coding it, so hopefully it makes a little sense. All right, and if the two currents were anti-parallel, we could show that the two wires actually repel each other. As you can see, will happen in this railgun. Okay, so does that make sense? Questions? Thoughts? A little bit of anger? Right. Well, careful. You're finding the force on B, right? The force on B from A, right? So when you write F on B, A, that's on B from A. So the from A is from that magnetic field due to that first wire, okay? And then the next part goes to find the force on the first wire due to that field. So let's read through it again, okay? So to find the force on a current carrying wire due to a second current carrying wire, comma, so to find the force on, the first thing you need to do is recognize that these two X's are wires going into the board, all right, or into the screen. So to find, so the force on this current carrying wire from the other current carrying wire, this is the second force on due to a second current carrying wire. So we must first find the field due to this second wire here, right? So the field from this wire onto IB, onto this wire. All right, the one I'm selecting now. So we use the Biot-Savart law to find that field. Then we find the force on the first wire. We find the force on this wire from the that is due to that field, right? So if we look back here, you look at our force law, right? F equals, the magnitude equals I, L, B, sine phi, or sine theta, right? So we know theta is 90 in this situation, and we're looking for the force on this wire. All right, so in order to do that, we have to find the field from this wire. So we can use our Biot-Savart law to get BA. All right, and that's the field. We want to find the field from this wire at this wire. Actually, I'm just going to pick a point there. All right, and you can see the field will be concentric circles. Will just be circles that get bigger and bigger until eventually one hits this wire here at IB. Okay, and then once we have the field, the magnetic field here, we can plug that magnetic field into our equation here, and that will give us the force of this on this wire from this wire B from this wire A. Okay? So I hope that makes some sense of it. You might want to watch it a few times and read it in the book. The book can be very helpful here. We're sort of getting to the point where, hold on, the magnetic field is circling the wire. Does the force due to the field also circle the wire? Are they always perpendicular? They will always be perpendicular. So the force isn't circling the wire. The force is straight this way, right? And the force down, basically you orient your wire so that the force will always be perpendicular. Notice BA in the picture. I'll erase everything so you can see it. You'll notice that the magnetic field, we look at it where it comes right down here, right? We're only looking at parallel and anti-parallel lines. And any straight wire will give you a circular magnetic field, okay? So no, there's force in other places, but we're only concerned about one point along the wire, and then assuming that that the force here would be the same as the force here. There's no reason why it would be any different, right? We're just looking at different lengths along the wire, So no, there would be forces in other places. We're just making it simple. But you might want to look at this, but we're kind of getting to the point, at least I think anyway. I have a feeling for a lot of you non-book warriors, or, oh, I don't need to read the book or anything like that, we're kind of getting to the end of physics 2, and there's no simpler way to do it. All the simpler ways to do it limit the scope of the problems we can solve. So, you might want to add that textbook to your arsenal if you have not already. And reading plus looking at the, you'll have the recording to go back and forth over, can be a big increase to your ability to understand this stuff. And again, like always, shoot me a Skype message and or stick around after class a little bit, and I can answer questions you might have. Okay. So speaking of which, we're getting near there. Let me see where I am. Okay, I'll introduce the next topic, but we won't go too far into it. Okay, because it's not. We only have about 10 minutes left, and I want to leave a little time for some questions and pondering. So the next topic we're going to talk about is a big one. All right, so it's good to cover it a little bit here and then review it and do our example Thursday. So The next thing we're covering is Ampere's law. All right. So remember I told you the real point of this class is to develop the 4 big Maxwell's equations. Well, we're seeing the first big equation we really had from this course was Gauss's law. And now Ampere's law is our second big equation that has to do with magnetism. Or that has to do with electrodynamics, rather. And Ampere's law gives us it's sort of like Gauss's law, but it is a bit different because it's not an area, it's not a surface integral, it's a line integral. And Ampere's law states that the closed circuit integral of B dot ds is equal to mu naught I enclosed. So instead of a Gaussian surface, you create an Amperean loop. All right, you'll notice you have 3 wires here. If you make a loop, only the currents inside the loop will count towards the magnetic field from this integral. All right. This is Ampere's law applied to an arbitrary loop that encircles 2 out of the 3. And note that the directions of the currents then the path you go along will when you go along in here, if they're opposite and equal, then you could have 0 enclosed current. That would be 0 B field. But you want to curl your right hand around the Amperean loop with the fingers pointing in the direction of integration. All right, so you have to choose this direction of integration. A current through the loop in the general direction of your outstretched thumb is assigned a plus sign, and a current generally in the opposite direction is assigned a minus sign. Let's read that again. A current through the loop in which the general direction of your thumb is outstretched is assigned a plus sign, and a current generally in the opposite direction is assigned a minus sign. So that means if you pick the direction of integration, right, get your thumb. You see the loop on the screen here. It's this. If you're curious or not seeing it, this is the Amperean loop. So put your hand around here and take your thumb out and follow around the curve. You'll notice I1 points in the direction of your thumb. So we're going to assign that a positive value. I2 points the opposite direction of your thumb. We're going to assign that a negative value. Okay? And notice that I3 is not in the loop and therefore will not be part of this Amperean surface. All right, this particular evaluation of Ampere's law. I guess we can go to the next one and then come back and review it. So when we do that, we can use Ampere's law right away to look at the magnetic field both outside and inside a straight wire. So if we look at the one example I want to end on is I want to show you the difference between using the Biot-Savart law and using Ampere's law. So Ampere's law is a bit easier, right? So if we have a wire, a long charge carrying wire, right? We'll make it positive. Well, we can't make it positive yet, right? We have to pick a surface of integration. So I want it to be positive, so that means I have to choose this direction to go around. This isn't a current. This is an Amperean loop. All right, I've picked the direction it goes. Now, when I look at this, I have B dot ds equals B times 2 pi r, because that is the length around the line here. It's 2 pi r, so you can pick something simple. And then when of course, you want to, in this case, it's very easy because B is always going to be, with the current, is always going to be in the same direction as the loop that we're going around. So that's going to make this a very easy evaluation of this indeed closed loop integral, right? And because cosine of 0 is 1, so we get this term, and then we can say that B times 2 pi r is equal to mu naught I enclosed. And you'll notice that all you have to do is solve for B, and you very simply get 0 pi over 2 pi r. All right, which if you recall from the Biot-Savart law, that's a bit more work, wasn't it? I'll remind you that that was 2 lines of math, basically. And in order to prove that with the Biot-Savart law, we had to do, well, all of this work, right? So, which one would you rather do, right? So I think that is a good place to stop because I want to review this tomorrow and go over it again. So it's good to just sort of see it and think about it. We'll talk about Selenium and things like that on Thursday. And we have an example we want to do. That'll take up most of our first hour. And then we have, we want to also look at this inside a straight line, but we can sort of make sense of that. But we'll look at that as well. So that'll do it for tonight. Let me take, I'm just going to find my phone so I can take the attendance. I'm going to stop recording so that the movie can process.